Hello, this is Mark Armitage coming to you from the microscopy facility in the biology department at California State University, Northridge. We welcome you to this series of training videos in confocal microscopy. The purpose of these videos is to train you on the Leica SP5 confocal microscope, which you will be using during your experiments for your projects. Now, we want to thank the Keck Foundation for their wonderful support of our department. Not only did they donate the funds which allowed us to purchase this instrument, but they also supported us in supplying the funds to be able to produce this series of training videos. These videos are hopefully going to accelerate your training. You can watch them over and over. There are quizzes you can take, and that will hopefully give you a foundation so that when you come in to work with the instrument hands-on, your training will be accelerated. During this series of videos, you will see a monitor behind me, a high-resolution monitor with images and text that are supportive of the concepts that we're trying to teach. The images that we're using on the monitor and in these videos are courtesy of Nikon Microscopy University. We want to thank Nikon and Nikon Microscopy University for the opportunity to use their images during the training portion of these videos. They have a wonderful website which you can Google, just Nikon Microscopy University, or go to the link that you see on the screen right now and take advantage of the host of tutorials, interactive tutorials, and training videos that they have on their website. Now, the Leica confocal microscope is a very complex instrument. It uses complex optics and lighting, it uses lasers for illumination, and it's a very software-driven machine. So before we start training you on the Leica, we're going to go to a standard compound upright fluorescent microscope to teach you the basics of optics, lighting, and fluorescent microscopy. We are going to begin our discussion of microscopical principles by using a standard compound microscope. Now, you're probably familiar with dissecting microscopes, which you've used in some of your labs to dissect organisms or other things. That's a very low power magnification instrument, and this is a different instrument. This is called a compound microscope. The reason this is called a compound microscope is because to get the resultant magnification out of the instrument, you multiply the magnification of the objective lens times the magnification of the eyepiece lens. Ergo, this is a compound microscope, and there's other features that we're going to discuss as we go along. Useful magnification for an instrument like this is about 2 power up to maybe 1200 power. You really can't go any higher than that and still maintain the resolution that you're looking for in a microscope. So let's begin with some basics, and you'll see a figure that I have here on the screen. And in this figure, you'll see yellow coloring, and that indicates the light path. And we'll be discussing how the light path travels through the compound microscope. And I'll be referring to this figure again and again. But let's begin over here with the microscope. Built into the stand in the base is an illuminator. An illuminator supplies light to the microscope. In this case, we have a tungsten halogen illuminator built into the base with a tungsten halogen bulb that burns very bright and very white. And that light travels from the bulb and the lamp housing up to a right angle mirror in the base, and then it comes vertically through the field diaphragm of the microscope. The field diaphragm is important, remember, because when we close it down, we can see it in the field of view, and it's also important for alignment. We'll show you how to perform that alignment in another section. The light travels through the field diaphragm and comes into the condenser. The condenser is an optical apparatus that does just as its name suggests. It condenses the light into a fine cone of light so that it can travel through the specimen on the stage and then into the objective. Each of these is an objective. Each one is highly corrected for the magnification that it produces and the resolution. We'll be discussing that more later. Then the light travels through the objective where all the useful magnification takes place. It goes into the nose piece, and you rotate the objectives by holding the nose piece on the knurled rubber band. It travels through the nose piece and up into the head of the microscope. This is called a trinocular head because you have 2 eyepieces for viewing and a third port to which you can attach a camera. Historically, we've used film cameras on the trinocular port, but nowadays, with the advent of digital microscopy, we can put digital still cameras on the microscope, or also video cameras which record live motion in living cells. We also have binocular tubes, and you may have seen monocular tubes in the past, but this one's called a binocular tube or head. We also want to discuss the illumination coming from above. We have transmitted light illumination through the microscope, and we also have reflected light illumination. In fluorescence microscopy, we use reflected light illumination. So let's discuss the components of the reflected light illuminator. Here we have a large lamp housing which holds a bulb that burns very brightly. Typically, these are called mercury vapor pressure bulbs. These are high pressure bulbs that must be handled very carefully because they can explode and destroy your lamp house. And this puts out a tremendous amount of illumination. We'll look at a graph on the screen later that shows you what's called the emission spectra. The amount of information or light put out by this bulb is a very high amount of light across a varying number of wavelengths. And that's important because when we do fluorescence microscopy, we have to use different colors to illuminate our specimen. We'll discuss more about this later. But the light travels from the lamp house through the vertical illuminator. It goes through an excitation filter, which is a specific color that's used to excite our fluorophore, which we'll discuss more about later. And you'll see this color in a second. It goes through the excitation filter, then it hits a mirror and is reflected downward to the specimen. So this is reflected light hitting our specimen. Then the light that is emitted from our specimen travels back through the objective, through the mirror, which passes it to the binocular or trinocular head. So if I push a set of filters into the light path, you'll see the bright blue light. What is this light? This is about 490 nanometers of light that it's being used to excite our specimen. We'll discuss more about excitation and emission later. But the light that comes off the specimen, or the emission light, travels through the objective and to the observer's eyepieces. This is very low light, and therefore you will often see a fluorescent microscope used in a dark room. Now we're going to go to the diagram and show you these features on the diagram as well.